Okay, so let's continue on into density. There we are. So we use that with a symbol rho. It has units that are kilograms per meter cubed. And if I was to draw this, it would look something like this. So there are two regions, region 1 and region 2. I'm reversing the numbers there. And if I look on one side, I have a whole lot more molecules. I don't like that. I'm going to use a different color. Let's do a different color here. Look on one side, I have a whole lot more. There we go, more molecules. And on the other side, I have just few. And so then I will have a density 2 and a density 1. In this case, density 1 will be much more than density 2, so as long as we're assuming that those two spaces are the same size. So what is density? Well, you could kind of say that it's how heavy a fluid is per unit volume. Per unit volume being the particular thing. Now we think about it as just simply saying how many molecules are stuffed into, oh goodness, into a particular space. As we learned from last time, the greater the density, the greater the buoyancy force, and also the greater the fluid forces you're going to be feeling. There's going to be more drag, there's going to be more friction as there's more molecules smacking into you. So we have to care about that. Then there's temperature. Okay. Temperature, capital T, units, typically Kelvin for us. You can also have Fahrenheit. We're going to stick mostly to Kelvin. Okay, now this is going to look similar to our pressure example because they are connected, but it's not exactly the same. So I'm going to have these molecules, all of them on either side, maybe less on one side, maybe more on the other. And I'm going to go ahead and say they have velocity. Maybe they're bouncing off the wall sometimes, and they're moving around. Now the bouncing off the wall does not matter here. What matters is how fast are these molecules moving. The faster they move, the faster, the higher our temperature is going to be. So temperature is how much kinetic energy your molecules have. And just so you know, this is based on molecular velocity, not on your flow velocity. You can actually have a very cold but very fast flow. Which I think all of you have felt at some particular points in time. So if I have, and I make this, let's just make it blue. And inside of here I have little, snowflakes. That is completely fine. That checks out. Okay. I'm liking the colors. I need to use more colors as I go through here. Just takes time, everybody. Takes time. Now, one thing to know before we go to our last one is simply that pressure, density, and temperature can all produce forces on objects. And they do that through their relation in the ideal gas occasion. Now, hopefully you haven't forgotten that already, but that's pressure is equal to density RT, where this guy is constant. So this is the big relation here for why they can all lead to forces. Okay, the very, very last one we're going to run into today is going to be viscosity. It's the one that you're probably the least familiar with. Maybe you're familiar with it, but I would say most people are the least familiar with this one. So let's go ahead and talk about it. So viscosity. Usually we have a mu for the symbol and units of Pascal seconds. Now how it works is the following. So I have some surface, and at that surface the velocity is equal to 0 because the surface is not moving. I mean, it can be, and then we change how we're doing this. And above that surface I'm going to have various little molecules, and they're going to be moving around. However, when those molecules move, they are going to be going from one streamline to another. So I have, U fast up here, I have U slow right here, and U mid in the middle. And when these guys go from one streamline to the other one, well, that means their velocity has changed. And if your velocity changed, it means there's got to be a force. And so this is where we get viscous forces like friction come into play. So the viscosity is a coefficient that represents fluid friction. So when those molecules jump streamlines, or another way of putting that is when they go from a part of the flow that is faster to a part of the flow that is slower, and vice versa, they have to change velocity. And a change of velocity leads to force. Because we know that F is equal to ma, which is equal to m dv dt. And this force we're going to have here is viscous force. But coming back to all of this, there's one thing to be very careful about, which is viscosity, or I should say viscous forces, require some sort of velocity gradient. So if we don't have a velocity gradient, we don't have viscous forces. Okay, so that's where we're stopping for this time. Thank you for listening. And next time we'll be going into some more details about, let's see here, what's next? Aerodynamic body forces and moments. So, see y'all then. Bye-bye.